Okay, let's begin. We are still in A2. Last time we learned about matrix multiplication. Which was a little strange to say the least, but we did a bunch of examples. And now we are going to continue. We're going to revisit the idea of an identity matrix. And now you're going to realize why it's called an identity matrix. So recall this is an n by n matrix called IN, which has ones on the diagonal and zeros everywhere else. So there are many versions. You can have many different dimensions. Of course, I1 is just that guy. I2 is just that guy. I3 is that guy, and so on. These are called the identity matrix. Now, why do we call this the identity matrix? Let me show you. Take C from the previous example, which we did last week. 1, 2, 3, 0, 2, 4. Now, what would happen if I computed I2 times C? See if you remember matrix multiplication. How would this actually go? First of all, is it possible to actually multiply those? How do we know it's possible to multiply two matrices?
On the inside, so we'll do like a 2 by 2.
So this is a 2 by 2.
2 by 3.
This is a 2 by 3. The insides are the same, then you can multiply, and the outsides give you the answer to the result. So the result should also be a 2 by 3. So now, how do you actually go about doing that?
First row, first column.
First row here times the first column, so it's 1 times 1 plus 0 times 0, and 1.
Then you go to the first row, second column.
First row, second column, that would look like what?
First row, third column. 1 times 3.
Move down, and now you do the same thing with the second row. Second row times first column, 0 times 1 plus 1 times 0. Second row times second column, 0 times 2 plus 1 times 2. Second row times third column, 0 times 3 plus 1 times 4. You can see everything is lining up. 1 and 0 is in the parentheses here, 2 and 2, 3 and 4. And the first row, 1, 0, 1, 0, 1, 0 is along the row, and the second row, 0, 1, 0, 1, 0, 1 is along the second row. So that will actually be the multiplication. Now, if I were to simplify this, what would I get? Well, that's 1 plus 0, 2 plus 0, 3 plus 0, 0, 0 plus 2, 0 plus 4. What did I actually get as the result here? I got C back. I got C itself. Right? In other words, multiplying a matrix by the identity gives you the identity of the matrix you multiply by. That's why it's called the identity matrix. It's kind of like how 1 is the multiplicative identity for the real numbers. Multiplying the number by 1, you get the number back. Right? We call this, therefore, we call the number 1 the multiplicative identity for the real numbers, and in the same way, In is the multiplicative identity in the land of matrices. It's the guy that when you multiply with another matrix, you get the original matrix back. Now, you might need a different I. This can work on either side, but you might need a different I. So for example, if you need Ci, you want to multiply in that direction, notice that you have 1, 2, 3, 0, 2, 4. And this would be a 2 by 3, which means in order for this to multiply, this would have to be a 3 here. So you need a 3 by 3 because the identity has to be a square matrix. Let's write this. So 3 here, 1, 0, 0, 0, 1, 0, 0, 0, 1. Do the multiplication. First row times first column. 1 times 1 plus 2 times 0 plus 3 times 0. First row times second column. 1 times 0 plus 2 times 1 plus 3 times 0. And first row times third column. 1 times 0 plus 2 times 0 plus 3 times 1. Now you do the second row. Second row times first column. 0 times 1 plus 2 times 0 plus 4 times 0. Second row times second column. 0 times 0 plus 2 times 1 plus 4 times 0. And the second row times the third column. 0 times 0 plus 2 times 0 plus 4 times 1. And then I can simplify that. 1 plus 0, 2 plus 0, 3 plus 0, all zeros. This is 2 plus 0, and that is 4 plus 0. And again, I get C. That's why it's called the identity matrix. Multiplying it on either side will give you the identity of the guy you multiplied by. And of course, because matrix multiplication needs to have these numbers lining up, as we just talked about last time, you might need a different identity on each side. So if you're multiplying on the left side, you need the 2-dimensional identity matrix. If you're multiplying on the right side, you need a 3-dimensional. Okay? So remember, matrix multiplication is not commutative in general, so the order does actually matter, and that will make a lot of difference. In general, square matrices will be the only one where the same identity on either side can work. So note, with square matrices, such as A in example 2, the same IN can be multiplied on either side. With similar results. In fact, you would realize if you took I2 times A, you will get the same as A times I2, which is A itself. And so this could be, this is a characteristic of the identity matrix. It's the guy that when you multiply any other matrix by it, you get the matrix itself. And that's why it's called the identity. Now, there's another important class of matrices that we want to talk about, and these are called the inverse matrices, the inverse of a matrix. So, yes, that's the next thing I want to talk about. So, let's talk about the inverse of a matrix. A square matrix has to be a square matrix, right? If it's not a square matrix, then this whole conversation is meaningless in the first place. A square matrix, A, is called invertible or non-singular. If there is another matrix say this is n by n. Another matrix B such that if you take A times B, you get the identity matrix, and if you take B times A, you get the identity matrix. If such a matrix exists, we call that matrix the inverse of A, or A inverse. And we write A to the minus 1 equals B. Alright, so this is notation. Okay? A to the minus 1. This is notation. So, as I mentioned last time, division is not a thing with matrices. There's no division operation. So, I want you to notice this does not mean 1 over A. Don't think of it like a laws of exponents kind of thing. It's actually a notation. It means the inverse. So anytime you see a matrix raised to a negative 1 power, it means the inverse of that matrix. Right? So it means there's some other matrix that does this. Now you might wonder where the name comes from and why the notation. In the real numbers, you can compare this. Compare to the real numbers. So you can say, for example, the inverse of 2 is 1/2, right? Or you can write it as 2 to the minus 1. Since you'll notice that if you take 2 and you multiply by 2 to the minus 1, you get 1, which is the identity for the number system, right? Multiply 1 by anything, you get the thing itself. So multiplying anything by inverse should give you the identity. And so we wanted the kind of the same thing to be happening with matrices, and so that's why we have these definitions. And the guy that behaves like the 1 in the matrices is the identity matrix IN. And sometimes you can have something like this. Not all matrices will do this, but sometimes you have a matrix where you can find something else to multiply it by, and you get the identity. So let me make sure to actually state that, because that's important. You shouldn't assume that every matrix has an inverse, because that's not true. No. Not all matrices. Not all square matrices have inverses. In the next section, you'll see inverses are very useful. We're going to use them in one specific way. In the next section, you'll see how we're going to use it. But right now, I want to talk about how you can find one. I'll give you a general method to find an inverse in the next section, but now I'm actually going to tell you specifically how to find one for a 2 by 2 matrix. So why? Because this one has a nice little formula that of course you'll be expected to memorize. So if you have a 2 by 2 matrix and it fulfills a certain property, you can find its inverse, and this is how. So here we're going to look at that inverse of a 2 by 2 matrix. It's very important that you realize what I'm showing you right now is only for 2 by 2 matrices. It does not work in general. Something like this does not work in general. So I'm going to show you a formula for 2 by 2 matrices. So this is just one that you're supposed to know because it's just a nice little formula if you're in the 2 by 2 case. And the more general case though, for like a 3 by 3 or a 4 by 4 or 5 by 5 or 6 by 6 or whatever number by whatever number, I'll show you a general method for that in the next section. But one thing you should know is you should kind of have the 2 by 2 one memorized. So here is how it goes. Let A, I'm going to call it A, B, C, D, be a 2 by 2 matrix. Here's how you know it has an inverse. If, right? So if this expression, AD minus BC, right? Multiply across this main diagonal here, minus, multiply across those numbers here, and you get this expression. It's actually called the determinant of the matrix, but that's not in our syllabus, so I'm not going to talk about it really at all. You'll see that in the next class. This expression, AD minus BC, if it's not 0, then A has an inverse. Right? If it's 0, it means A does not have an inverse. And in fact, we know what that inverse will be. In fact, A inverse in this case will be equal to the following. 1 divided by AD minus BC, which is why it can't be 0, of this matrix. Here's how you're going to figure out the matrix here. You're going to swap the guys on the main diagonal, and you're going to change the sign of the other two. And that gives you the formula for the inverse of a 2 by 2 matrix. And such a matrix will exist if this expression is not 0, which allows you to even compute this formula in the first place. Now, let me actually show you an example. And we're going to prove that it is a matrix. Use to find A inverse. A is defined in example 2. So we did a bunch of examples with these matrices over here. I keep using them throughout the whole section. So the A in example 2 is this guy. Find A inverse. So here you have a 2 by 2 matrix. I want you to find its inverse. So what you're going to do is first you can do your little check. If you look at AD minus BC, this means this times this minus this times that. That is 3, which of course is not 0. That's good. Okay, so we know this guy has an inverse. There are some other 2 by 2 matrix that when I multiply by this guy, I will get the identity. What matrix is that? This matrix. So let's actually compute it by the formula. The inverse matrix will be equal to 1 over AD minus BC. That. Now that is 1 over, well, this expression which I just computed, 3 times the matrix. I'm going to swap these two numbers, which they ended up being the same. And then I'm going to change the sign of those two numbers. So this is going to be a +1 and a -2. And so that will be 1/3, 1/3, -2/3, 1/3. That is A inverse. Seems like a very strange guy, but let's actually check. I take A times its inverse, recall from a few minutes ago, A times its inverse should give you the identity. And A inverse times A should give you the identity. Right? That's how you can check. This is how you would check that something is actually an inverse. So let's actually do the check. If I were to take A times A inverse, here my A is 1 minus 1, 2, 1, and my supposed A inverse is this guy. Now clearly these can be multiplied. This is a 2 by 2, that's a 2 by 2. So what I'm going to do now is I'm going to do the rules. First row times first column. That's a 1 times a third plus a minus 1 times minus 2/3. First row times second column, that's 1 times a third plus a minus 1 times a third. Now the second row times the first column, that's 2 times a third plus 1 times minus 2/3. Second row times second column, 2 times a third plus 1 times a third. If you were to simplify this a little bit, you would get 1/3 plus 2/3. Here you would get 1/3 minus 1/3. Here you would get 2/3 minus 2/3. Here you would get 2/3 plus 1/3. And if you simplify that, you will get 1, 0, 0, 1. So when I multiply these two, I get the identity as the result. Now, I'm going to save you some work here. There is a theorem that says basically a n by n is invertible, then if you take A times this is the identity, then I'll use that phrase, if and only if A inverse times A is the identity. In other words, if one of these equations hold, so will the other. So you only have to check one. I'm not going to show you the proof of that, but this is something you know. So technically the definition says both of these equations have to be true, but it turns out with how we're using matrices, it will always work out that if this one is true, that one's automatically true, and vice versa. So technically you only need to check one, so I decided to check the one on the left here, and that actually works out, and so that's actually enough. So I can say this matrix is the inverse of that matrix. And you can also say vice versa. This matrix is the inverse of that matrix, because if I multiply one by the other, I get the identity matrix. We'll see why this is very convenient pretty soon. For now, I just want you to know what that is. We're still in a slight definition series here. So A1 was, section A1 was all definitions. Here, I taught you how to multiply. These are more definitions of things you need to know. We will get to the point where we're using them though. And I just want to copy these down. So here are some properties of matrices. In other words, the algebraic properties. So you need to know what's legal versus illegal for matrices because some things, not everything is obvious, right? We saw that last week, right? When we were adding guys, it felt very natural. Subtracting, yeah, it feels very natural. Then we went to matrix multiplication. It's like, what? Craziness, right? So there are some things that seem to make sense and some things won't seem to make sense. So you need to know what are the legal moves for you to make when it comes to matrices because sometimes they act like they're numbers, but sometimes they don't. Like matrix multiplication is not commutative, for example. So they can behave a little weird. So let's talk about the properties of matrices. Now, all of these can be proven. I'm not going to prove them for you. I'm just going to tell you what they are. So let A, B, C be matrices. Let I be appropriate size identity. Zero is the appropriate, right? It matters what size everything is. Everything with matrices is very particular. Is the appropriate size. Zero matrix. Let K be a scalar and assume the following operations. Are defined. Okay. Then the following properties hold. A plus B, it turns out, is equal to B plus A. So it turns out matrix addition is commutative. So matrices, you can add them in any order, right? Now again, it might not seem like, oh, surprising, but there are some things that can be surprising, so you should know. It's also associative. So we have addition is commutative. Commutative means the order does not matter. It's also associative. So if you have three matrices to add up together, it turns out you can choose to add either two first. So if you want to add three matrices A, B, and C, you can add A and B and then add C, or you can add B and C, then add A, you'll get the same result. This is a different property called associativity. Addition is associative. Nothing strange so far. Addition and scalar multiplication kind of work the way you'd expect. Nothing really strange. Three, A plus 0 is actually equal to A, and 0 plus A is actually equal to A. So if you add the 0 matrix, it doesn't change anything. 4. Okay, now here's something that's very strange. A times B is not the same as B times A in general. So here's the first strange thing. These might seem obvious, but it's because you're not really you might still be thinking of things as if they're numbers, right? These guys are not numbers, they're matrices. They have very different rules. And for one of them, multiplication is not commutative. You can't just swap the order, right? If you're multiplying something on the left, you have to multiply it on the left, right? So if you're trying to solve a matrix equation and you want to multiply something on both sides, like you're solving with a regular equation, the order in which you multiply is going to matter. So if you multiply the right side on the left by something, you have to multiply the left side on the left by something. If you multiply it on the right, you're wrong. Because you can't swap the order in multiplication. It turns out multiplication is associative though. So if you want to multiply three matrices together, well, you multiply either two first, in line, and you'll get the same answer, 6. And this is a definition that I put before. AI is the same as IA, which is the same as A, 7. So multiplication is the one you have to look out for. Okay. Now, here. A times B plus C is equal to A times B plus A times C. And B plus C times D is equal to B times D plus C times D. And that means this is a distributive law. And again, let me warn you here, order matters. Right? So if you wrote DA or CA or DB or DC, you're wrong. The order matters. The B is on the left, the D is on the right. It must have the B on the left, the D on the right. The C is on the left, the D is on the right. It must have the C on the left, the D on the right. The order matters a lot, right? Don't make this mistake. So I wrote this down. It might look very normal to you, but it's not normal. It's very rigid how it has to be applied. So pay attention to these rules, because if you don't apply them carefully, you can get in trouble. Because once you mix up the order of things, you're now getting different answers. Or sometimes you might not even get an answer at all. We saw that last week, where we multiplied two matrices in one order and we got an answer, but if we swap the order, suddenly it's undefined. Right? So you can get into a lot of trouble by not paying attention to what side you're multiplying things by. The thing is, constants can kind of weave in and out. So if you have Ka times B, so K is a number, and we already looked at what that means, then it turns out you can actually move the K in the middle. So when it comes to a scalar multiple, the order doesn't matter. You can multiply on either side, you can move it in and out of matrices. And 9 is just a definition of invertible. So, and you can even think of it as this. So you can first find AB and then multiply that result by K. So when it comes to scalar multiplication, you have a lot of options. And here, A is invertible. Means A times A inverse equals I, and A inverse times A equals I. So those are the properties. So when it comes to addition of matrices, remember one thing for addition though. The matrices have to be of the same size. We looked at that last time. Matrices must be of the same size. So they must have the same number of rows and columns. For multiplication, they don't have to be of the same size, but the dimensions must line up a certain way. The inner numbers must match up, and the outer numbers give you the answer. Right? So when it comes to addition, it can kind of be sloppy. It'll kind of work out how you expect it to work out with real numbers. So all of that is fine. When it comes to multiplication, though, you have to be very careful. The order is going to matter. So you can't be sloppy and just write things down however you want. The positions that you're writing things down in will matter a lot. Now, to end this section, this is at the end. We're going to introduce the idea. The main reason why we want to use matrices is going to be to solve equations. In fact, to solve very particular kinds of equations. Now you might remember this. I'm going to write it down in a very specific way. Recall definition. A linear system of equations set of equations in n variables. Let's say that is a set of equations of the form one plus one, two plus two, three plus three, plus a1n times n equals 1. So that is the first equation, that's the linear equation. The a's are constants here. The variables are the x1, the x2, the x3, the x4, right? If it's just like 3 of them, we normally call it x, y, z, but it could be many of them, and then we just use x with subscripts to represent the variables. And you can have a second row, 2, 1 plus 1, 8, 2 plus 2, 8, 2, 3, x 3, plus 8, 2, n equals 2. So you can have another equation, and you can continue like this until you get to the last line, the last equation. Like that, so you can have a list. You will notice here we have m equations. And there are n variables. So here, where the x1, x2, xn are variables, and the a, I, j are constant coefficients. Now, when you have m equations and n variables, you call this an m by n system. When we have m equations and n variables, we call this an m by n system of linear equations. So, some examples. Example. I can say 2x minus 3y plus 4z equals 7. X plus 2y equals 9. And x minus 3z equals 17 is a 3 by 3 system. Notice I have 3 variables. And I have 3 equations. I can also do something like 4x1 minus 7x2 plus 3x3 plus x4 equals 9. And do x1 plus 2x3 minus x4 equals 15 is a 2 by 4 system. Notice here, I have 4 variables, and I have 2 equations. Now, it turns out systems like these appear more often than you would think. Our goal is to solve these systems. So ultimately, you want to get to a point where, given such a set of equations, you can actually solve for them, solve for the variables. Ultimately, our goal is to be able to solve these systems. What does it mean to solve these systems? That is, find values for the variables. That will work in all the equations at the same time. So to solve the system means, can you tell me what x, y, and z have to be so that all three of these equations make sense at the same time? Right? That's the goal. Right? That's what it means to solve the system. So someone's going to say, oh, make x equals 1, y equals 7, and z equals 4, and then all of these will be true. Right? That's not the solution to this, of course. I'm just giving you an example. That's your goal. You want to find values for the variables. Not just so that it works one place, but it has to work in all of them at the same time, right? If this can be done, we say we can't solve the system. If a solution can be found, technically they define this in the other section, but I'll just mention it here. If a solution can be found, the system is called consistent. If there is no solution, meaning no matter what list of numbers you tell me, there's no list that will work in all equations at the same time. If there's no solution, it is called inconsistent. So a consistent system is one in which I can find a solution. I can actually give you a list of numbers that will work in all equations at the same time. Inconsistent means I can't do that. No matter what list I come up with, none of them are going to work. Or I might be able to get some of them to work, but not all of them. And that's a problem. The solution requires that all of them need to work. So a little bit of definitions there. Why do we care about matrices? Well, here's how. One of many reasons. Like, it's unbelievable how useful matrices are. Can't be understated. Overstated. Okay, now, here's something interesting. Let's say consider a system. Consider the system blah. So A11 x1 plus A12 x2 plus da 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 plus A1 n xn equals B1 A21 x1 A22 x2 plus da 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 A2n xn equals B2 da 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 M1 x1 plus A M2 x2 plus A M n xn equals B n. Notice here we can put each side in a matrix, right? When I start plugging these guys in, this expression is just going to give me some number. In fact, I want it to add up to that number. On the other side, this is a number. So I can actually just, you know what, let's just throw these in matrices. I can say that this is equal to that. E1, E2, M, and I've got A11 x1 plus da da da, the A1n xn da da da, the AM1 x1 da da da, the AMN xn. I can just throw both sides in a matrix. This works by matrix equality, right? One side will be equal to the other side. Corresponding components will be equal. right? This works by matrix equality. But we can do something further. Now, this one's going to be kind of strange when I first write it down, but in hindsight, you should be able to see that via matrix multiplication, you can write the following. I'm just going to write it down, and then you're going to see. If you actually do the multiplication operation, you'll actually get the previous line. It turns out I can throw all the coefficients in one big matrix, line them up. A11, A12, A1n, A21, A22, A2n, all the way down to AM1, AM2, AMN. And I can put all the variables in a matrix, x1, x2, all the way down to xn. And then this side is just going to be that b1, b2, all the way down to bm. Turns out I can actually write the system like this with matrix multiplication. And how would this work? Of course, if I take row times a column, what am I doing? I'm taking this times this, plus that times that, plus that times that, plus that times that, plus that times that, all the way down. That would recreate this equation. Right? Similarly, when I take the second row times this, this times this, plus that times that, plus that, I'll create the second equation. And I can keep doing this all the way down to the last one. Take the last row times this column, I'll get this times this, plus that times that, plus that, I'll create the last equation. So it turns out I can go from this situation to that situation. So I can actually use a matrix to represent the system. Now, this guy here is called coefficient matrix. Why? It's the matrix of all the coefficients. Take all the coefficients, throw them in a matrix, make sure everyone's lined up. This one is called the solution matrix. Because basically, when we want to solve a system, this is the guy we need to solve for, right? That's like your variable, that's like your x, right? I need to tell you what should x1, x2, and all these guys be in order to make everything work out. This is called the constant matrix. And there are very customary variables here. This is what they're commonly called. You would call the coefficient matrix big A. You would call the solution matrix X with a little arrow over it. And you'll tend to call this guy B with a little arrow over it. So the above has the form AX equals B. This is called a matrix equation. So this is called a system of linear equations, but every such system I can transform it into a matrix equation. I can write it down, I can express any system with using matrices in this form. Put all their coefficients in a matrix, put all the variables in a matrix, put all the constants on the other side of the equation in a matrix. And we would have formed what I call a matrix equation. Now, did I give any examples? Okay, I gave us a stupid one. Well, let me just write it down anyway. It's just a 2 by 2. example. If you see x minus y equals minus 1, 2x plus y equals 4, that is a 2 by 2 system of equations, has 2 variables and 2 equations. This can be expressed as, well, like that, where I later take the x coefficients, I would take them in order. So the coefficient of x is 1, coefficient of y is minus 1, coefficient of x here is 2, coefficient of y is 1. I can actually represent this system of equations by that. And then I can say, oh, this matrix I will call A. That is my coefficient matrix. So from this I can extrapolate, we can extract A equals 1 minus 1, 2, 1. So I can look at a system like this, and this matrix will now become important to me. Now I care about this particular rectangular array of numbers. You will also notice that that is the A that I used in the previous example. That's on purpose. I'm going to show you one way to solve a system, and we're going to look at another way in the next section. Now, hopefully all of you know how to solve a 2 by 2 system, like automatic in general, like from, I don't know, from the previous class. But we're now going to look at matrix methods of solving a system. Here's one way to solve a system. There's a theorem that says the following. Suppose A is invertible. That means I can find its inverse. Then the equation AX equals B has a unique solution. It means there's only one set of numbers for X and Y that I will plug in and will work in this equation. And it is given by X equals A inverse times B. This is a theorem, very important term to know. If a matrix is invertible, you can actually solve a system where that matrix isn't the coefficient matrix by just taking the inverse of the matrix and multiplying by B. Now, why does that work? Well, why? Well, if AX equals B, what that means is I can multiply by A inverse on the left. Multiply both sides on the left by A inverse. Now what's going to happen? Well, A inverse times A is the identity matrix. And the identity matrix times any other matrix is just the matrix itself. And so I end up with the X must be that expression. Let's actually put this in action on this little line. Here, of course, A is 1 minus 1, 2, 1, and A inverse exists. In fact, we found it, right? We know that A inverse was, it was 1/3 minus 2/3, 1/3, 1/3. Was that it? We found that before. What this means is I can solve for the x. I can solve for the variable in this matrix equation over here. This means that the x value, which in this case is the xy, is equal to this guy, 1/3 minus 2/3, 1/3, 1/3, times this guy. Now let's actually see what that gives us. Matrix multiplication. Wait, can these be multiplied? Well, we can check. This is a 2 by 2, this is a 2 by 1. So yes, the inner numbers are the same, so we can multiply them. The result should be a 2 by 1. So what will that 2 by 1 be? Well, it's going to be 1/3 times minus 1 plus 1/3 times 4. And then it's going to be minus 2/3 times minus 1 plus 1/3 times 4. You can simplify that. That's minus 1/3 plus 4/3, that's 3/3, which is 1. Here you have minus 2/3, but you have plus 2/3, plus 4/3, that's 6/3, that's 2. i.e., what I'm saying is, if you set x equals 1 and y equals 2, this solves the system. That's one way to express the answer. You can also express it in matrix form. Right, matrix equality tells us corresponding components are equal. So the x is equal to the 1, the y is equal to the 2. That's strange. Does that actually work? Let's check. If I plug in 1 for x and 2 for y, that gives me minus 1. Yeah. What if I plug in 1 for x in the second equation and plug in 2 for y in the second equation? That gives me 4. That set of numbers solves both equations at the same time. X is 1 and y is 2. Now, this is just to illustrate to you that this thing actually works, what we just built. Now, ordinarily speaking, if you're faced with a 2 by 2, you're just going to do it the way you've always done it, right? Things become a lot harder when the system starts getting a lot bigger, right? You're not going to want to solve something directly by hand when it's like 7 equations and 8 variables. Now it's like, okay, what am I substituting? What am I going to eliminate? Who am I adding to who? What's going on? It gets very confusing. But if you can just reduce that to a problem about matrices, then all you have to worry about is coefficients, and you can use matrix multiplication and finding inverses and just moving these numbers around, which would be easier in general once you get the hang of it, and you'd be able to solve a system. Be able to do a lot more things than that, but the scope of our class goes this far, right? We're going to show you enough about matrices, and not even everything. We're going to show you some things about matrices that you can use to solve a system. There are many other things that you can use with matrices to solve systems. There's a lot of things you can do with determinants, for example, which we're not going to talk about at all. But inverses, using inverses is one way that you can solve a system. If your coefficient matrix happens to be a square matrix that has an inverse, you can find the answer to the system of equations that that guy represents by simply multiplying its inverse by the right side with matrix multiplication. You'll get your answer. Okay. That ends this section. We're going to see more ways to solve systems in the next section. We're also going to see ways to find inverses when you don't have the 2 by 2 case. break, so I guess we'll keep going. A3 is going to be the next section. We're going to learn some more techniques here. And yet another way to represent a system of equations. We're going to learn something very technical. This section is called solving systems. That's the main goal of this section. I'm going to show you how to solve systems. I'm going to show you a technique called row reduction. Using that technique, I will show you how we can find inverses and the echelon forms. A lot of things done in this section. By the way, a lot of computer algebra systems and even your calculators a lot of the times actually use matrices and row reductions to do some of the calculations that you're doing. It's much easier for the calculator to just manipulate an array of numbers. So you'll be surprised. A lot of those things that you're punching into your calculator is like, wow, like magic, you know the answer. Your calculator is computing matrices in the background. Right? Programs like MATLAB do that all the time. Wolfram Alpha does a lot of that too. A lot of times if you type into Wolfram Alpha a system of equations, it translates it to matrices and it solves it as matrices. And then it tells you, hey, here's the answer. Now you're going to actually learn how to do that by hand. In case you were ever curious. How is this calculator doing this? How are you doing this calculator? I'm going to show you. This section is going to show you how the calculator calculates things. How does your calculator solve equations? So, recall from last time, we can write a system of linear equations in matrix form. So that means like AX equals B, where this represents something that looks like this. List of equations. So it represents a list of equations that we want to figure out a common solution for. There's another way to express an equation using matrices. Sometimes you want to express the entire system with one large matrix. And this is how your calculator would do it. And for this, we ignore the variables since we can identify them. By their positions. So I can take an entire list of equations and I can just express that as one huge matrix. Where here's how the matrix is going to be created. First of all, your calculator isn't going to do this, but you as a human being would do this. You're going to draw a line on one side. This line represents where the equal sign is. So you would have a list of numbers over here representing these guys, the right side of the equation, representing the constant matrix. Now on this right side, you're going to put the coefficient matrix. So you're going to have that A11, A11, all the way down to A1n, A21, A22, all the way down to A2n, all the way down to AM1, AM2, all the way across to AMN. So pretty much you represent the matrix, the system in this form. A with a bar, and you put B beside it. So you just replace this list of equations with one big matrix, where in your head there's a divider that's dividing where the equal sign is. And this, by the way, is called the augmented form of the system. This is called the augmented form. Okay, so you can have an equation form, you can have a matrix form, and you can have what we call an augmented form. And when you put a matrix, a system of equations in augmented form, you can say you augment the system. So you might see problems in your homework or on a test that says, hey, augment the system and do blah. When they say augment the system, they mean write it in this form. When you write the system in augmented form, we say we've augmented the system. Example, let's go back to our silly example from before. We can augment this and write it as, well, one big matrix, the bar, I'm going to put 1, minus 1, 2, 1, minus 1, 4. Now this matrix, whenever you see a bar inside of a matrix, it means that the person who wrote that matrix down was specifically thinking about it as a system of equations, right? Where the bar is going to represent where the equal sign is. Now, you don't express any variables, you have something like this, you just write it as a huge rectangular array of numbers. And that's because you order the variables in their columns. Notice that the first column of numbers is always with the x. The second column is always with the y. So it's understood that everyone in the first column represents the variable x1. Everyone here represents x2, and so on and so forth, all the way down to xn. The columns themselves represent the variables. I know that the first column represents the first variable, the second column is the coefficients of the second variable, the third column is the coefficient of the third variable, etc. So you never actually write them in. You write down all the numbers. The numbers are the things that you care about here, right? The names of your variables doesn't really matter that much anyway, right? If I replace x with a and y with b, solving the system would give me the same numbers. The actual names of the variables is irrelevant. It's superfluous information. You don't actually need it. So this tells you everything important about the system. It tells you you want to add 1 times one variable minus 1 times another variable to get minus 1 as the answer. And you need 2 times the first variable plus 1 times the second variable to give you 4 as the answer. And so this can represent the system. This says the system is in augmented form. This is all in notes, by the way, but I just wanted to show you. Do we get how I'm setting up this form here? Like, if you don't know where some number I'm writing down is coming from, you should ask me. Especially if this is the first time you're seeing it, it's okay to be confused a little bit. First time I saw it, I was confused a lot by a lot of things, but it takes time. Okay, so now let's actually look at solving a system in augmented form.
So like in like the answer, we just leave it alone like that, like if it just says augmented form, we just leave it like that, we don't solve anymore?
No, this isn't the solution. This is just me expressing the equation in another form. So normally you would augment it in order to find the solution, right? So this is just, you're taking it from the land of equations to the land of matrices, and you're going to solve it in the land of matrices. Right? So this is just really the first step to a problem. Okay. Let's actually solve the system. Now, let's look at 2x plus 3y equals minus 1, and x minus 2y equals 3. Now, I want to illustrate to you what these row operation things are that I'm going to talk about. So, I'm going to solve this kind of in the old way you're used to solving it, but I'm going to do it very roundabout. It's going to seem like I'm beating around the bush. Just plug in the answer. But there's a purpose, because I want you to be able to compare something to it directly. In fact, hopefully I'll have enough space to actually put them side by side. Overly long. Okay. So I'm going to be overly long on purpose here, but the point is to illustrate something to you. So we're going to use the process of elimination to solve this equation. One catch is, at any given time, I do want to have both equations. So you want to think of it as if you're a computer. You have to keep all the information in your memory all at once. The moment you only write down one equation and not the second one, you forget it, right? So we're always bringing with us a pair of equations. So that's the first rule. Now the second rule is, I'm going to use the process of elimination just like the way we've always used it. We want to eliminate some variables so that we're left over with the variable that we want. So I'm going to actually perform that. Okay. Now, let's say this one, for purely aesthetic reasons. Suppose I want, I don't like the fact that 2x is on top. I want 1x on top. What I just did was, I swapped the equations. Right? There's nothing wrong with doing that. Sure, why do I need to do that? I don't need to do it. I just like the fact that I want a 1 to be in the top left corner. Okay? So what I can do is here, I can swap the equations. Okay, cool. What else do we want to do? Now, suppose I wanted to eliminate the x and solve for the y.
Multiply.
1? Yeah, exactly. You would multiply, right? What I can do is I can multiply this equation by 2 and then subtract that one, right? So let me actually do that. So I'm going to here 2x minus 4y equals 6. So this is equation 1 times 2. Then I would have 2x plus 3y equals minus 1. I'm just bringing that along.
Why didn't you multiply it by minus 2? Why did you multiply it by 2?
I could have done that. It wouldn't have mattered. It wouldn't matter in the end, actually. Minus, plus, minus, multiply by minus. Okay. Now what we can do is we can now add them, right? So what I did here, I want you to just be very careful what I'm doing. I multiplied 1 by 2. Multiply equation 1 by minus 2. And what I'm going to do now is I can add them to eliminate the x. Now, I'm going to add these guys, and I'm going to put the result in the second equation. So, This plus this, it's 0x. This plus this is 7y. This plus this is minus 7. Now, what I want to do is put back the nice form of the first equation back in the top. Right? So I'm always keeping the pair of equations. So I temporarily changed this one for the purpose of eliminating that guy, but then I put him back after I eliminated that guy. Right? But I still have the two equations. So what I did here was add the equation 1 to equation 2. And that I put the result here in the second, keeping the first one tagging along the whole time. Now what you can notice is that here I have 0x plus 7y equals minus 7. I can actually solve that for y right away. I can just divide this equation by 7. So that's what I'm going to do next. So here's the top equation, x minus 2y equals 3. And then I would have 0x plus y equals minus 1. Here I just divide by 7. So now I have that pair of equations. Now, one thing you can notice here, we could stop here and just plug the y in there and solve for x. Let's continue. Anyway, let's continue and bring this to a nicer form where I can look at both equations and I can immediately tell the answer for each variable right away. So clearly the second equation tells me the answer for y, right? I clearly have y equals minus 1. Okay? So I know y equals minus 1. But remember this equation, remember this spot. It's going to be important. We're going to actually give this spot a name. There's going to be a spot where we can solve it, but it will require a little bit of work to continue to find the solution, but we can continue further. So remember this spot. Let's label it star. Let's continue. So now I have an equation that is very convenient for me in terms of the y value. I can use that equation to find the y value. Now my goal is try to do something very similar for the x value. Try to create an equation so that x is the only one in play, where the coefficient of the y is 0, so I can just say x equals blah, right? That's the goal now. And I'm going to do that goal in pretty much the same way I did this, right? So I want to multiply one or both of these equations by something convenient, so that when I do this addition thing, one thing will cancel out. Now, if I want the x, my goal is then going to be to cancel the y. So what I can do is I can multiply this equation by 2. Right? So here I have x minus 2y equals 3. I'm going to multiply the second equation by 2. So I did here, multiply by 2. And it becomes that. Now what I can do is I can add these. And I'm going to put the result in the top. Add 1 and 2, and put the result in the first line. X plus 0x is just 1x, minus 2y plus 2y is 0y. This plus that is 1, and then I'm going to just copy this one back. And so now, notice in the second equation, I can say x equals 1 and y equals minus 1, right? So this is the important spot. This spot tells us this stage gives us the entire equation immediately. The entire solution immediately. We'll call this double star. So ultimately from this I can talk about the solution. I can say x should be 1 and y should be minus 1. So I can go through, using the process of elimination that we're used to, I can ultimately get to a nice form of the answer. Sure, I wrote down more than I had to, but it was for comparison. So I could swap two equations, wouldn't make a difference, the answer is not going to change. I could multiply an equation through by some number that's not 0. Notice that if I had multiplied by 0, everything, I would lose all this information, I wouldn't be able to solve the system. But I can multiply by any non-zero number, and then I can add any two equations to make a new equation. Here, I divided by 7, I can think of that as multiplying by 1/7. Here again, I multiply by 2. Here I added the two equations to get a new equation. Notice here that there are three things that I did. There are three principal things that I could do on my way to solve the equation in such a way that I don't destroy the solution by doing them. I can swap equations. This is one thing I'm allowed to do. I can multiply an equation by a non-zero number. This is another thing I'm allowed to do. And I can add two equations. I can add a multiple of one equation to another equation. This is a third thing I'm allowed to do. I can do three things, and in this way I can legally solve a system of equations by doing these three things. Okay, so I wanted to emphasize the three things that I'm doing. Because when you go to matrices, those are exactly, you have an analogous set of actions that you can do. There will only be three things for you to do that are legal at any given time. Don't do one of these three things, you are wrong. Okay, so that's one way you can solve a system. Now, let's solve it in augmented form. So, I'm pretty much going to copy what we did here. Now, in augmented form, this guy would look like the following. 2, 3, minus 1, 1, minus 2, 3. Okay? That's how my system starts. Now, the first thing I did was I swapped the two equations. But the rows represent the equations. So swapping two equations is swapping rows. So I put this row on the top, and I can move that row to the bottom. So that's one thing I could do here. Swap rows. Okay. So now we're in this scenario. Ultimately, I want to be able to solve for this guy, which means I want the coefficient here to be 0, I want the coefficient there to be 1. That will give me the equivalent thing of an equation that tells me who the second guy is. But to get there, what I can do is, I want to eliminate this 2, because my goal is to find this guy, I want to make this guy 0. I'm going to multiply this one by 2, or negative 2, if you prefer. Now, something I took to do 2 steps here. When you get used to this, you'll be able to do it all in 1 step. But I'm going very slow now because we've just started.
Can you do that? Wait, what did you just do for the third part?
Okay. So, it's good, and I'm going to start doing it now, to label what you're doing so you never get lost. You can always track what you're doing and understand fully what you're doing. So, to keep track, I'm going to keep track. Label each matrix by positions relative to previous matrix. There are other ways you can write this down, but I find this is my preferred way, and I think it's a very nice way to use. So ultimately, what we can think of this is as row 1, this is row 2. So to actually describe to the reader what I just did, I can say row 2 and row 1. So now you can see what I did. row 1 from the previous line is now moved into the position of row 2, and row 2 from the previous line is now moved into the position of row 1. I just swapped the two rows. What did I do here? Well, row 1 from the previous row, I multiplied by -2. And row 2 from the previous row, I didn't do anything. Right? So my markings here are referring to the positions from the previous position. Right? So I took row 1 from the previous matrix, multiplied by 2. Row 2 from the previous matrix, I didn't do anything. Right? So the rows of row 1 and row 2 are changing the whole time I'm doing this. Okay? So that's one thing I can do. But this represents the second operation. I can multiply a row by a non-zero number, which is what I did here with the row 1. Now I'm going to do the third thing. I'm going to add the rows, and I'm going to put the result in the second row. So what I'm going to do here is I'm going to take row 1 and add it to row 2. That is going to result, -2 plus 2 is a 0, 4 plus 3 is a 7, -6 plus a -1 is a -7. And I have a row that looks like that. Now, the previous row, I multiplied by -2 to get it in a convenient form to kill this guy, so now what I'm going to do is I'm just going to divide it back by the -2 to bring it back to the smaller numbers. Right? Same thing what I did here. Now clearly I'm in a position to clean this one up a bit, so I could move to something like this, 0, 1, -1, by just taking row 2 divided by -7. And then I had this. Now the goal is to do the same thing in the first one, in the first row. I want to create a situation where there's a 1 here, there's a 0 here, and there's an answer. Because that would tell me exactly what the first guy was. So what I would do is multiply the second row by 2. And I would leave row 1 for a second. I'm going to start using the same color after a while. This is 1, -2, 3. And now what I'm going to do is I'm going to add row 1 and row 2. And I leave the over 2 and I divide this back. So ultimately what I'm going to have now, 1 plus 0 is 1, -2 plus 2, 0, this plus that is 2. And 0 plus, and then I'm going to put this back, 0, 1, -2. Was this what we got last time? Oh, I didn't multiply this by 2. And so now that plus that is, like I said, what you're doing is simple, but it's easy to make a mistake, so you have to be careful. Now, ultimately, you see now I'm in a very special situation. One thing you will notice is that the left side of this augmented matrix looks like the identity matrix. Goals, right? Whereas the right side just has a list of numbers. What do these numbers mean to me? Well, they're going to tell me what the meaning of what the value of each variable is. The first one, the first row tells me that 1x plus 0y equals 1. In other words, x equals 1. The second row tells me 0x plus 1y equals -1. In other words, y equals -1. So this is equivalent to the second star position that I had over there. And this one is equivalent to the 1 star position I had over there. Now clearly at this point I could have actually stopped the process, say y equals -1, plug that into the first equation and solve for the x. But I wanted to go to a nicer situation, right? So here I had the ability to solve the equation. One thing I want you to realize in how I knew I had the ability to solve the equation is that my 1's cascaded off to the right, and any variable that had a 1 in it before has 0's in it in lower rows. So that means that variable is not in play in any lower row, and so I could do this back substitution operation to figure out everyone at some point. So that's the first step. Now, here is where all the definitions come in. So again, it's a simple example. I know it makes the 2x2 system more complicated, but I did it extra long to show you all these things that I'm about to describe. Now, in the previous example, three legal operations are called row operations. Why? They're operations I did on the rows of a matrix. There are three row operations. There's what we call a type 1. This says we can swap two rows. This is a move that you can do with an augmented matrix that will not affect the solution of the system it represents. Type 2. You can multiply one row by a non-zero constant. It's a second type of row operation. Type 3. You can, I'm going to say this in a very specific way. It's very important that you remember it in the specific way for some theoretical things that will come later. But I guess for now, you don't have to think of it this way. You can just think of it as adding one row to another. But I'm going to state it in a very specific way because in the future, if you go to the next class and they're going to be describing things, it's going to depend on you remembering this in a very particular way. But this is basically the guy that says you can add two rows to eliminate something. So replace one row, replace a row by itself plus a multiple of another row. For us, basically what I'm just saying, you can add two rows together to eliminate something. Now there are cases in which you don't really want to think of it in that sloppy way, you want to think of it specifically in this way, but in Math 2009, you're never going to be in a situation where really need to know it this way, but I just want to make sure I state it in the way that if you remember it this way, all your future math classes, you don't have to relearn anything. That's going to be the way they're going to be thinking about it. So there are three row operations. Now, these are the only legal moves one can make when solving a system with an augmented matrix. So it is important that you know there are only three things you can do. So at any time you're working with a matrix, which in the next test and on the final you'll be working with matrices, and you're like, would it be nice if I can just take this and divide everyone over there? Illegal. You cannot divide one row by another. You can do 3 things and only 3 things. The moment you don't do one of these things, you're doing something wrong. You can swap a row, you can multiply a row by a non-zero number, and you can add 2 rows together to eliminate something. Anything else you can think of, anything else that comes to your mind, it is wrong. Everything else is illegal. Okay? There are only 3 things. 3 and only 3 things you can do with an augmented matrix. These are them. Everything else is illegal. These are called the row operations. Now, let's talk about these situations here, the star and the double star. These are called echelon forms, or they're examples of echelon forms. The form star is an example of a row echelon form, which I will abbreviate REF. The form double star is an example. I'm going to describe these guys in detail because you'll need to know how to put a matrix in these forms. The one there is called a reduced row echelon form. REF. Both are the convenient forms. Needed to solve a system. So, the situation where you look as close to the identity matrix as possible on the left side is called reduced row echelon form. The situation in which you are above the diagonal, you have non-zero numbers, but you have all zeros below the diagonal, or something similar to that. We'll talk about that more in a bit. This is called a row echelon form. So that's row echelon form, reduced row echelon form. Here you can't get any better than this. This is the gold standard. And usually when you plug in a system of equations into your calculator, it throws it into a big matrix and it reduces it to this form, and then it tells you this is the answer for the first variable, that's the answer for the second variable. Right? But those are called row echelon form and reduced row echelon form. These guys are the convenient forms. Once you can get to either one of these, you can solve the system. Now, one thing is there are times when you will specifically be asked to find the reduced row echelon form on a test or a quiz or a final. It's on the final. And you saw it was actually on the bonus on the test today as well. I see to find a row echelon form. Now you kind of know what it is. I'm going to define it exactly. One thing to note about the row echelon form is this form is not unique for a given matrix. This one, though, this is unique for a given matrix. And that's why anytime on a test or a quiz or a final, I will ask you to go to this form, or the final will always ask you to go to this form, because it's possible for everyone to do everything right, and everyone has an answer that looks different here. But if everyone goes all the way to here, everyone's answer needs to be the same by the time they get to this point. This is the best possible scenario that you can have. Everyone will have the same matrix. Whereas it's possible to have a row echelon form that's different for a given matrix. You can have multiple ones. And so just to make sure the answers are consistent, you'll often be asked to go to the reduced row echelon form, so that when they put a multiple choice answer, they know there's only one answer that they need to actually know is the correct one. definition to tell you everything that's going on in the title. There's a lot of kind of theory and definitions in this section too. The process of using row operations, i.e. the thing I was doing just now, that process of using row operations to achieve REF or RREF is called row reduction. So that's where the title comes from. It's called row reduction. Specifically, row reduction or elimination and specifically these forms are so important that they each have their own special name given to the process to achieve them. If you go to the REF form, you did the process that's called Gaussian elimination. Right. So if someone says, use Gaussian elimination to solve this system, it means you can stop at the row echelon form and then just plug in the answers. If you go to the reduced row echelon form, if you take the extra mile, you go the extra mile, you did what we call Gauss-Jordan elimination. So you'll see these phrases. They both refer to row reduction. They're given a special name because it indicates to you where the operation stopped. So if you stop before you get to the perfect nice form, you said you did Gaussian elimination, and if you went all the way to the completely reduced form, you said you did Gauss-Jordan elimination. But these are both examples of row reduction. Right? This whole process of me doing these three operations to transform a method into a nice form is called row reduction. So essentially, when I solve this system, which I had over here using the matrices, you can say, I used row reduction to solve the system. Right? That's the method. Right? And if I had stopped in the first nice form, I would say, oh, I did Gaussian elimination to solve the system. And if I went all the way down here to solve the system, I'd say, oh, I did Gauss-Jordan elimination to solve the system. Just the name of all these things. But the important thing is, of course, yeah, I mentioned everything here as well. The important thing is to realize that, and I also did things side by side here. I think I actually did less steps here than I did on the board. But, yeah, I mentioned all of these. And I also did it side by side in here, explain to you what I was doing. But the thing is, if you're reading something, these are words that will pop up in a question or something like that, so you need to know what they mean. Right now, I'm going to specifically tell you what it means to be an REF or RREF. Or maybe I'll tell you that after, because we're pretty much out of time now. And so we'll continue at 1:15. So that's just what we call these. I'm going to specifically define that later because you're going to be required to actually put matrices in these forms. So you'll see on some of the finals where it says, oh, here's an augmented matrix, put it in reduced or echelon form. That will be like a question that you'll be asked. Okay. So that basically what that means is you're going to do a process like what I did here to bring it all the way to the point where it pretty much looks like the identity on the left side. But we'll stop this now. Take a break.